In modern high-frequency trading, processing a signal in fractions of a microsecond is standard practice, but the probability that a pristine trading intent actually survives the journey from a research model to a venue acknowledgement is dropping. For years, firms have attacked latency by deploying highly specialized hardware. We see kernel bypass NICs and FPGA switches shaving nanoseconds off local processing times. These optimizations operate in strict silos and have reached a point of diminishing returns. The primary threat to profitability is no longer raw speed. It is cross-domain variance, the unpredictable friction that occurs when independently optimized components fail to coordinate. You might have the fastest feed handler on the market, but if it routes through a network path experiencing brief congestion, or hits a server dealing with noisy neighbor-host contention, or waits on saturated shared storage, that local speed advantage dissolves. A microsecond delay past a venue deadline erases the entire value of an otherwise perfect trading signal. In these environments, missing the time window converts the opportunity into a total loss. Raw packet speed cannot guarantee a profitable execution if the broader infrastructure remains structurally uncoordinated. This diagram illustrates the topology of a highly optimized yet disconnected quantitative trading stack. On the left are the specialist components: feed handlers, kernel bypass layers, FPGA switching, and native RISC or OMS systems. A sub-microsecond switch excels at moving data, but it cannot independently manage a sudden CPU spike on a downstream host, nor can it detect if the precision time protocol has degraded, feeding stale timestamps to a pricing model. This creates a requirement for the Predictive Tensor Control Plane, or PTCP. It operates as a cross-domain, topology-native connective layer that links the state and outcomes of these isolated systems. Connecting these domains targets three specific outcomes: accelerating research velocity, assuring execution reliability, and maintaining resilience during failovers. Crucially, this control plane does not generate trading signals or alter order economics. It operates entirely as an overlay, coordinating existing Ethernet, host, storage, and trading interfaces. The objective is alpha retention. By keeping the entire research-to-market system inside a verified operating envelope, firms preserve the fraction of opportunity that infrastructure variance usually destroys. This chart maps out the standard event-to-wire path, from a market event through feed normalization, strategy intent, risk checks, gateways, and finally to a venue acknowledgement. Between these nodes, cross-domain attribution breaks down. A specialist feed handler normalizes data perfectly, but does not know the downstream queue pressure at the network gateway. Transporting packets quickly through this chain is actively harmful if the underlying market state is stale or the time basis is compromised. A localized latency spike, perhaps a momentary processing delay at the risk gateway, can cascade downstream, ultimately causing the intent to miss its critical time window. The metric that matters here is the valid, timely intent rate, the percentage of strategy intents that remain unchanged, pass all native risk checks, and reach the designated outbound interface before a hard deadline. System health is determined by the survival of those unchanged intents reaching the wire on time, rather than the isolated benchmark of any single piece of hardware along the way. This block diagram details the full PTCP reference architecture, separating predictive control from operational action. At the top, the observation plane ingests time-aligned metadata, like timing, dependencies, and queue states, while strictly avoiding proprietary strategy logic. Below that, the predictive slow path analyzes cross-domain relationships to preemptively identify anomalies. Recommendations then pass through the authority and safety gate. Every proposed control must be cryptographically signed, scoped to specific resources, versioned, and time-bounded. Approved controls are handed to the bounded fast path for execution through existing interfaces. Finally, the evidence loop records the outcome, verifying success or triggering a safe rollback. By physically separating complex analytical reasoning from bounded reversible execution, PTCP intervenes in a live environment without introducing unmeasured risk. Implementing dynamic infrastructure controls introduces a severe engineering tension. Optimizing a path must never violate authoritative pre-trade risk systems. The architecture relies on a strict non-replacement principle. PTCP does not invent a parallel market access path or suppress required venue safeguards. When a PTCP control signal encounters a native order management system or pre-trade risk boundary, the native rule vault acts as a hard stop. The dynamic optimization actively yields to the established risk parameter. This strict hierarchy is required to maintain alignment with the SEC market access rule and MiFID II obligations, ensuring that a firm maintains absolute, documented control over its market access. The system functions purely as a coordination layer. It enforces existing compliance boundaries rather than attempting to supersede them. This same cross-domain variance affects the upstream quantitative research pipeline. Firms invest heavily in compute clusters, only to encounter severe data-to-simulation bottlenecks. Measuring the success of a research platform by looking at raw GPU utilization or total submitted job counts is a statistical trap. A cluster can run at maximum capacity while producing slow, irreproducible results. This model outlines the end-to-end research acceptance pipeline, flowing from data availability on the left through feature execution, validation, reproducible acceptance, and production readiness. When datasets are not properly localized, or storage I/O is saturated, or noisy neighbor contention interrupts a job, the backtest becomes operationally invalid. The PTCP coordination surface addresses this by aligning job admission with validated data. The true economic denominator for research infrastructure is the volume of accepted, reproducible outputs per constrained resource, not how busy the processors appear to be. This scatterplot maps specialized point products by their local versus cross-domain scope. Kernel bypass adapters and FPGA switches dominate the lower left, highly effective but restricted to local components. PTCP occupies the upper right quadrant, executing bounded, closed-loop actions based on the aggregate topology. The commercial posture is strictly complementary. A firm maintains its specialized hardware and its packet-derived analytics. The control plane integrates their telemetry and manages their dependencies. Owning this coordination gap is the necessary engineering step to extract the maximum return on investment from existing hardware deployments. Infrastructure upgrades in electronic trading require strict causal attribution. Value must be proven against measurable execution outcomes, not marketing anecdotes or generic packet metrics. This chart details the ascending commercial ladder for deployment. Autonomous control is earned through progressive safety gates, moving from initial shadow observation to human-approved recommendations, and finally advancing to a tightly bounded canary action. This timeline shows the required 90-day procurement proof. Every step must be completed and independently accepted before multi-site scale is authorized. Throughout, value is proven using counterfactual baselines, matched cohorts, and holdout runs to isolate the exact retention value. In a mature electronic trading market, raw speed is commoditized. The ultimate competitive moat is continuously converting infrastructure variance into protected research and verified execution.